this is Captain Chaudhari. In the series of videos on basic ship stability calculations, I was doing this SFBM. I found one typical problem that's from my book. I thought I will share that problem with you. It's a little different from the other box vessel SFBM questions that we did. The question says that there is a box vessel 80 meters long and it has got 4 identical holds, each of length 20 meters, and the breadth of the box vessel is 10 meters. Now, if we say this is hold number 1, then 2, 3, 4, right? So this side is forward. There is 1048 tons of cargo over here, 1048, and then this is 931 over here, and then 1227 and 1314. Now it seems that the cargo is level trimmed in all the holes, right? Now this box vessel floats in salt water, and we know that length of the vessel, that is 80 into 10 into mean draft into 1.025 should be equal to the load displacement. It seems the draft is 6 meters, the mean draft is 6 meters, so let us find out what is the displacement. 80 into 10 into 6 into 1.025 equals 4920, and let's total up the cargo. Cargo is 1048 plus 931 plus 1227 plus 1314. Total cargo is 4520, and therefore the light weight should be equal to 400 tons. Light weight is 400 tons. It's given in the question that the mean draft is 6 meters and the vessel floats in salt water. So indirectly they have given the light weight of the ship being 400 tons. So total buoyancy force is 4920 over a length of 80 meters. So 4920 divided by 80, this is buoyancy per unit length. So 4920 divided by 80 gives me buoyancy per unit length as 61.5 meters. So we'll write down the data here. The light ship is 400 tons and buoyancy per unit length for 6 meter draft is 61.5 meters. It is given in the question that the forward draft is 5 meters and aft draft is 7 meters. The vessel is trimmed by 2 meters. Otherwise it can be found out with no much difficulty if we say that the center of flotation of the vessel is midships. So the moment that is caused by 931 over this distance and moment that is caused by 1048 over this distance will give me the forward trimming moment, and this weight multiplied by this distance, which is 10 meters, and this weight multiplied by this distance, which is 30 meters, is going to give me aft trimming moment. Aft trimming moment minus forward trimming moment will give me resultant trimming moment, and this resultant trimming moment can give me what is the trim. Now MCTC can be found out very easily because MCTC is WGML upon 100L. GML is approximately equal to BML, and BML for a box vessel is L square upon 12D. But we are not going to those details. We assume that the given draft 5 meters and 7 meters is correct. So the ship is trimmed stern by 2 meters, forward draft is 5 meters, aft draft is 7 meters. So this is part of the question. Now if the buoyancy per unit length should depend on the draft, and at 6 meters draft the buoyancy per unit length is equal to 61.5. So If the draft here is 5 meters, 6 meters, 7 meters, the draft at this point should be 5.5 meters and draft at this point should be 6.5 meters. So at 6 meters, if the buoyancy per unit length is 61.5, so at 5 meters, the buoyancy per unit length should be 61.5 into 5 divided by 6. Right? So 61.5 into 5 equals divided by 6 gives me 51.25. So buoyancy per unit length at 5 meters draft is 51.25 and the buoyancy per unit length at 5.5 meters in the similar way will be 61.5 into 5.5 equals divided by 6. That gives me 56.375. 5.5, 56.375. Similarly, the buoyancy per unit length at 6.5 will be 61.5 into 6.5 equals divided by 6 gives me 66.625. And for 7 meters, it is going to be 61.5 into 7 equals divided by 6, that is 71.75. 71.75 tons per meter. At any given point, if we want to find out what is the load per unit length is buoyancy per unit length minus weight per unit length. So if we call this point as A, middle hold is B, and C, D, E, F, G, H, I. So at A, the load per unit length should be equal to 51.25, and in the bracket, what is the light weight per unit length? If the light weight is 400 tons, 400 divided by 80 will be 5, plus cargo 1048 tons is distributed over 20 meters, so cargo per unit length is 52.4. At C, in hold number 1, because C is representing the end of hold number 1 and beginning of hold number 2. So at the end of hold number 1, it will be 50, buoyancy per unit length is 56.375 5 plus 52.4. So we have 51.25 minus . Now let's go to the next hold, and for the hold number 2 at position C, we have the buoyancy as 56.375, the light weight is 5, and the cargo in hold number 2 is 931 divided by 20, that is 46.55. So it will be 56.375 minus 51.55. That gives me 4.825. Next we have the point E in hold number 2, and we have the buoyancy per unit length as 61.5 minus 5 plus 46 point Now the point E in hole number 3, it will be 61.5 minus 5 plus, it is 1227 here, 1227 divided by 20 gives me 64.85. 25 minus 5 plus 61.35. So it will be 66.275. And 66.625 minus 5 plus 1314 divided by 20 gives me 65.7. So 66 gives me minus 4.075. And then finally at I, it is 71.75 minus 5 plus 65.7. That gives me 1.05. So these are the values of the load curve. I can write these values of load curve over here. At C, inside the hole number 1, it is minus 1.025. In hole number 2, it is 4.825 and 9.95. And in hole number 3, it is minus 4.85 and minus 0.275. And hole number 4, it is minus 4.075 and 1.05. Now if we want to fit this 80 meters long ship in 16 meters page, so I can take a scale of 5 meters is equal to 1 centimeter. This is a scale of length. And now I can see the values going up to 9.95. Yes, so probably I can take 1 ton per meter is equal to 1 centimeter. That is the scale I can take. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tons per meter. This is the load scale. And minus 1, 2, 3, 4, minus 5, 6, 7. Okay. Now about the length, it is 5 meters is equal to 1 centimeter. So can I say that 80 meter is fitted in this length? So these graduations, they represent each hole, and each hole is 20 meters, and here is each centimeter represented in this diagram. So A, B, C, D, E, F, G, H, I. So from here to here is 1, 2, 3, 4 centimeters and 20 meters of the ship. So 5 meters is equal to 1 centimeter. Load scale, that is 1 ton per meter is equal to 1 centimeter, and the horizontal scale is the length scale. The scale is 5 meters is equal to 1 centimeter. So we put the values at A, it is minus 6.15, 3, 4, 5, 6. Over here, 6.15. The value at C within hole number 1 is minus 1.025, minus 1.025 over here. From here to here, the curve will run as straight line because the cargo is level trimmed. At C within hole number 2, the value is 4.825, 4.825 would be something like this over here. And E within hole number 2, the value is 9.95. So the curve would go like this. Now in the hole number 3, the value at E is minus 4.85. That means the curve is going to come down over here. And within the hole number 3, the other value is plus 0.275. Plus 0.275 would be something like this. And then in hole number 4, the value is minus 4.075 like this, and then the value goes to 1.05. So here in this diagram we have the load curve that is drawn to the scale. Now the load per unit length in the hole number 1 was minus 6.15 and minus 1.025, which is indicated like this. And because the cargo is level trimmed, we have a straight line from A to C. If we take the mean of the two values, we'll get the load value at B. Similarly, if we take the mean of these two values in the hole number 2, we will get the load value at D. Right? Similarly, you can say that in hole number 3 the value moves from minus 4.85 to plus 0.275, and we can find out the mean value, right? But we will see that later on. And in the hole number 4 it is minus 4.075 till here. Now when we make the shear force and bending moment diagram, more than the accuracy, what is important is the shape of the curve. If the shape of the curve is correct, that means the candidate has a good idea of the shear force and bending moment. So we will give more focus on that part, like where the load curve is going upwards, the shear force curve will be curvilinear with the center of curvature up. Here also, in this region also, load curve goes upwards. The center of curvature of the shear force curve will be up. Same thing over here and same thing over here, right? All through the shear force is going up, the load curve is going upwards, so shear force will have center of curvature upwards. Now to find out the shear force values, at various stations, say station A, the shear force is 0 because area under the load curve, right? Area under the load curve to the left of point under consideration is the SF ordinates. So to left of this point, there is nothing, no area. So shear force at A is 0. Shear force at B can be found out by finding out the area of this trapezium. The area of this trapezium would be 3.587 plus 6.15 equals divided by 2, and that is to be multiplied by the distance between the two lines, that is 10 meters. That gives me 48.685. So at B it is 48.685. At C the value will be the area of this trapezium from A to C. So 6.15 plus 1.025 equals divided by 2 equals into 20. That gives me total area 71.75. Now the value at D will be the area of this trapezium, and that is 4.825 plus 7.3 4.387 equals divided by 2 equals into 10, that is 61.06. Mind you, these values are negative, and when I have this positive area as 61.06, that will have to be treated with minus 71.75, minus 71.75, giving me the value as minus 10.69 at E, that is at this point. Let us find out the area of this trapezium. So that is 7.387 plus 9.95 equals divided by 2 into 10, that is 86.685. So that will have to be treated with minus 10.69 minus 10.6 gives me 75.995. This is plus 75.995. Now I will draw the shear force curve up to here and explain you a few principles of drawing the shear force curve. First of all, let us decide the scale. Probably the shear force value is going to be maximum at this point where the previous curve is changing the sign. The previous curve is crossing x-axis or changing sign over here also, and here also, and here also, but they will be all peak values. The maximum value appears to be here, and the maximum shear force appears to be 75.99. So we should have a scale to fit the shear force curve in the same graph, but approximately taking the similar dimension. So we can take the scale of shear force as 10 tons is equal to 1 centimeter. So shear force, which is measured in tons, will be 0 here, 10 here, and then 50 here, and then 70 here, and so on. So the value is 75.99. So we start with 0 for the shear force curve, and we go to minus 48.685. So that is minus 50 is over here, 10, 20, 30, 40, 50. So minus 48.685 is the value at B. And at C, the value is minus 71.75. Minus 71.75. So the value at C is over here. And the value at, first of all, let me draw this curve. This curve cannot be a straight line because the previous curve is slant straight line. And I have to draw from A to C in such a way that the center of curvature is up. So the curve goes like this. So this is the shear force curve. Similarly, the value at D is minus 10.69. So minus 10.69 is over here. And the value at E is 75.99. So 10, 20, 30, 40, 50, 60, 70. 75.99 would be like this. So, and mind you, the curve goes from here to here in such a way that it is curvilinear, but the center of curvature is not down, it is up. So I might draw the curve this way, showing the center of curvature that way. Now I want to find out what is the peak value, because I know the peak is going to occur at this point. Peak is going to occur at this point, which is about 8 meters from the diagram. Approximately, I say it is 8 meters from here. So this distance is 10 meters and this is 8. So this is 18 meters. And what is the area of triangle? Half base into half. So half into 18 into the height is minus 4.85. So 4.85 into, that gives me minus 43.65. So this area is minus 43.65. So far, the accumulated value of the shear force, that means adding up the area under the load curve, was 75.99, and I will treat minus 43.65 with 75.99. I get 32.34. I will not call that point as G. Maybe I can call this point as G dash. So at G dash, I found out the value is 32.34. So at this point where the load curve is crossing the axis, the value is 32.34. 10, 20, 30, 32.34 could be something like this. So the peak value appears to be here. So from here I have to move to this point in such a way that the curve center of curvature is upwards. Now this small value could be considered as the height over here. The value over here is 0.275. So 0.275, if the height of the triangle is 0.275 and this distance is suppose 2, and we want to find out the area of triangle, so it will be 0.275. So hardly any change compared to this, but the curve is changing in upward direction. So let us say we are going to have a peak over here. So at G it would be plus 0.27, 32.61 plus. Let us find out the area of this triangle. This side appears to be 17. This is only approximate. And the height is 4.075. So the negative area is 17 into 4.075 equal divided by 2 gives me 34.63. This I treat with 32.61 plus 32.61 gives me minus 2.075, minus 2.075. Now let us find out this positive area. This positive area is half multiplied by 3 into 1.05. This is the positive area. So 3 into 1.05 equals divided by 2 gives me the positive area 1.575. When I treat with this value minus 2.075, I get at I a value which is approximately equal to 0. This means I need to have a peak value here which is on negative side. The curve should come like this, center of curvature upwards, and from here once again I should move to 0 with the center of curvature of the curve upwards. So this is how the shear force curve can be drawn. So when the examiner checks your curve, he sees that the previous curve is going upwards, right? And throughout you have drawn the shear force curve with the center of curvature upwards. Very nice. He sees that the previous curve is having a peak value over here. Previous curve is changing the direction from positive to negative or negative to positive. We have peak value for the next curve, maximum peak value. And you can see here itself, here also you have the peak value, then you have a peak value over here also, and finally the shear force that starts from 0 ends to 0. For the shear force curve also, we can see approximate positive area appears to be equal to negative area. That is true for the load curve also. For bending moment curve, we cannot say that the positive area should be equal to negative area. We are going to expect the peak value of bending moment or maximum bending moment at this point. We can read from the graph, this is 10 meters, 20 meters, 30 meters, and probably 32 meters from the left side or forward side, we are going to have maximum bending moment. And if we want to find out the value of the maximum bending moment, we need to find out the area of this part of the SF curve by Simpson's.